Assalamualaikum and hi everyone. So today we are going to learn about 1.2 resolution of forces in the chapter Force and Motion 2. So here in this diagram, you can see that two boys are playing tarik upih. One boy is pulling the upih and another one is being pulled. So the direction of pulling force is actually inclined upward. But the motion of the boy that is being pulled is horizontal. So why does this happen? So this situation can be explained by resolution of forces. So the definition of resolution of forces is the process of resolving a force into two components. Okay, so here in this diagram, we can see that one single force, as indicated by the red arrow here, which can be resolved or it can be split into two components, which is horizontal component and vertical component. So let's do some exercises. Number 1, draw the horizontal component and vertical component of the forces below. So here what I have in the exercises is just the direction of forces. Okay, so some applications can be as already shown in the diagram above. Okay, so for example, number 1, maybe a boy playing tarik upih. So the direction of force is inclined upward. But we just leave all the diagrams, all the unrelated diagrams. So we just take the single force. Okay, so now we can split the force into two, which is horizontal and vertical. So we can label these forces as, so this is the pulling force, the horizontal force is Fx, and the vertical force is Fy. Okay, example number 2. So the direction is force is downward, inclined at downward at certain angle. So maybe in real life example, maybe we have a lawn mower trying to push his lawn mower. Okay, so the direction of force here can be split into two, which is downward, Fy, vertical component, and to the left, which is the horizontal component. Next, number 3, we can split into horizontal component, which is to the right, and vertical component, which is Fy. Okay, so next, once we identify the direction of the forces, the vertical components and the horizontal components, we must calculate the magnitude of the components using triangle method. Once you have split the single force into two components, you can form a triangle. Since these forces are vectors, we can move the vectors around as long as the length is not changed. So here, what I'm going to do is I am going to move Fy to the right side so that I can form a right angle triangle. So here I have on the right side is right angle triangle. And from this diagram here, I am going to find the magnitude of Fx and Fy. Okay, so based on the right angle triangle here, we must identify sin theta and cos theta in order to find Fx and Fy. So sin theta is opposite over hypotenuse. So opposite of the angle theta is Fy over hypotenuse, which is F. So to find Fy, make it as a subject and you will get F sin theta. Similarly, to find fx, you must use cos theta, which is adjacent over hypotenuse. So from the diagram, the component adjacent to theta is fx, and the hypotenuse is f. So to find the horizontal component fx, make it as a subject and you will get f cos theta. Okay, let's do some real life example. A woman is mopping with force F at an angle theta from the floor. Number 1, label the horizontal force Fx, vertical force Fy, and force F, which is the pushing force by the woman. Okay, so we know that the direction of force by the woman is indicated as the blue arrow here, and then we can split into two components, which is Fx to the right and Fy, which is downward. So there you go. Next, number 2, write down the function of horizontal component and vertical components in terms of theta. Okay, so first you have to identify where theta. Theta is the angle between the mop and the floor. Okay, so in this diagram, theta is here. Okay, next, you must form a triangle. Okay, so this is the triangle of force. And don't forget to label your theta. And label your Fx and Fy. So from here, it is easier for you to identify your horizontal component and your vertical component. So first, if you are not sure to use either sin or cos, you can just derive both and identify later. So first, cos theta is adjacent, which is Fx, over hypotenuse, which is F. So from this equation here, you can identify the horizontal component, which is Fx, equals to F cos theta. So this is the function for horizontal component. Next, similarly, we have to do for vertical component. Sin theta equals to opposite of theta, the component opposite to theta, which is Fy, over F. Make Fy as the subject and you will get F sin theta. So this is your function of vertical component. Okay, let's do example number 2. So this one is a bit tricky because the object here is on an inclined plane. Okay, so let's start. A box with weight W is stationary on an inclined plane at an angle theta from the floor. So let's label theta. Identify and label the weight W, weight component parallel to the plane, which is Wx, and weight component perpendicular to the plane, which is Wy. Okay, so take note, in this situation, we no longer use horizontal or vertical. Instead, we use component parallel to the plane. So we expect that the component must be drawn parallel to the plane here. And another one is a component perpendicular to the plane. So we know that it should be perpendicular, which is 90 degrees to the plane. Okay, so let's erase and do properly. Okay, so I'm going to draw on the diagram itself. First, you have to label weight. So weight is a force acting downward. So we can label it as W. So this is your single force. So your single force is acting downward, and you must split it into you must split the component into two. Okay, so we expect it should be split here and here. Okay, first we have to split it into a component which is parallel to the plane. So draw a line parallel to the plane. Okay, so that is one component which we call as WX. And then the second one is draw a component perpendicular to the plane. Then draw another line which is perpendicular to the plane, 90 degree to the plane. So there you go. Now you have two components that is resolved from one single force. Don't forget to label SWY. Okay. Next, write down the function in terms of theta. Okay, so from this diagram, one thing that you should know is the angle theta here. Okay, I am going to label with white pen here. So theta here is actually the same as the angle between W and WY. Okay, so now you can form a triangle. Okay, so I'm going to form a triangle here. Let me transfer it to the right side so that you can see clearer. Okay, first draw a straight line which indicates W, and then I am going to maintain the position of WY. So the vector force that I am going to move is WX. So the component that I highlight in yellow here, I am going to move it to here so that I can form a triangle. So simply just draw a line here which indicates WX. So now you have a right angle triangle. So this is 90 degree between WX and WY. And there is your right angle triangle. So don't forget to label your theta as well. Theta. So now you must find WX and WY in terms of theta. So if you are not sure to use sin or cos, just derive both. Okay, let's say you want to use sin first. Sin theta is equal to opposite. So the component opposite to it is WX over hypotenuse, which is W. So WX is W sin theta. So do the same for cos theta, which is adjacent to the angle WY over hypotenuse, which is W. So to find WY is actually W cos theta. Okay, so take note that WX here is the component which is parallel to the plane, and WY here is actually the component perpendicular to plane. So in the next video, we are going to continue with real life problems. Thank you.